Let's now look at an alternate way to implement Prim's algorithm, which is actually doable in an interview if you had to implement Prim's algorithm. So what I've shown here is basically the same code that we had in the previous video for building the graph. So I'm assuming that we are given n, the number of vertices in the graph, whose IDs are conveniently ranging from 0 to n minus 1, and I'm assuming that we can build an adjacency list for those n vertices out of the connections array, which is basically a list of edges where each edge is essentially a triplet indicating the source, destination, as well as the weight on that edge. So we build the graph as before, and then we initialized the captured array as before. So the captured array will be a one-dimensional array of size n initialized to -1, and we are again choosing vertex 0 as the source vertex for beginning our algorithm. So we'll assume that it already lies in the left partition, which is why its captured value is set to 1. And then we're going to have a priority queue as before, which will initially store all the neighbors of vertex 0. So we will traverse the adjacency list of vertex 0 and insert each neighbor of vertex 0 into the priority queue as part of the initialization, and the priority value associated with each neighbor is basically going to be the weight of the edge between that neighbor and vertex 0. So this part is also identical to what we had in the previous implementation. And we are again going to have a total cost variable, which is going to record the cost of the spanning tree or the growing structure as it is growing, which will eventually become the spanning tree at the end of the algorithm. So all this initialization should look familiar from the previous video, and now we come to the core body of the algorithm, which is this while loop. While the priority queue is not empty, what are we going to do? So like before, we are going to pop the priority queue. We are going to do an extract min operation, which will return to us a node with some priority value. This is what we will get when we do an extract min operation or a pop operation on the priority queue. Now this is where a difference is going to come in between the current implementation and the previous implementation. So the problem with the previous implementation was that if we had this this node that we capture and we look at all its neighbors in the adjacency list of that node, it's possible that one of the neighbors could lie here in the same captured set, in which case we don't do anything. But it's also possible that one of the neighbors could lie undiscovered here, in which case we add it to the priority queue with a priority value equal to the weight of this edge. It is also possible that one of its neighbors could exist here, already existing in the priority queue with some priority value, and then we have to compare the weight of this edge with that priority value to see if we can improve the priority by means of a decrease key operation. Now when we had a decrease key operation available, we would resolve any multiplicity here, right? If there are multiple vertices pointing to the same node in the priority queue, we could compare the weights of those multiple edges and settle for the lowest possible weight as the priority if needed, using the decrease key operation to reset the priority. But now that we don't have a decrease key operation, what are we going to do? Well, it seems that we have no choice now but to insert the same vertex multiple times in the priority queue with different priority values. So suppose this is let's say vertex V. If we had, let's say, 3 edges coming into it from the left side with weights, let's say 1, 2 and 3, every time we see an edge going into V, we would have inserted a copy of V with the priority value into the priority queue. So the priority queue would actually store 3 copies of the vertex V with 3 different priority values. This is the only way to avoid a decrease key operation, to reinsert the same vertex multiple times with different priority values. Now, how are we going to handle the fact that the same vertex v is going to get popped multiple times from the priority queue? Well, the first time that v is popped from the priority queue will be the time when we are actually pulling on the lowest cost edge, the lowest cost cut edge into v. So it's really that first extraction of v which is the most important for us as far as building the spanning tree is concerned. Any later extractions with higher priority values or higher values here for the priority field, these have no importance to us, because once we have captured v, we don't want to keep capturing it again and again and again. We don't want to create cycles in our growing tree. The event that matters to us most is the event when v is extracted for the first time, which is going to be the time when we extract it with the smallest priority value. That means the lowest cost cut edge into v. So this means that every time we extract a node from the priority queue, we have to make sure that it's a meaningful extraction. If that node has already been extracted before, we don't care about what we just extracted. So when we pop and we get this node comma priority value from the heap, we want to make an additional check here to see if the node has already been captured before, right? If the captured value of node is already 1, right? I'm just writing that in English here. If the node has already been captured before, in code you would say if captured of node is already equal to 1, then we don't care about this edge at all. We just continue. Okay, this is like a no-op. We drop that edge and we go back to the beginning of the while loop and extract the next entry from the priority queue. So when we come here, we know that the node is being extracted for the first time, and so we set the captured value of node to be equal to 1 here. Now we are going to look at all the neighbors of this node. So for each neighbor, and remember the neighbor is found with the cost of the edge to the neighbor, so for each neighbor comma cost pair in the adjacency list of that node, we have 3 options. The first option was that the neighbor was already captured, in which case we don't do anything. The second option was that the neighbor is undiscovered, in which case it needs to be added to the priority queue with a value equal to the cost. And the third option was that the neighbor already exists in the priority queue, but now we can't go and look up what the priority value there was or decrease it. What we will do is we will insert another copy of the neighbor into the priority queue with this with the cost written on its on the current edge. So notice that regardless of whether the neighbor is undiscovered or whether it lies already discovered and sitting in the priority queue, we are going to insert a new copy of that neighbor into the priority queue with a priority value equal to the cost. So that means we don't need to differentiate between this scenario and this scenario. All we need to do is we need to differentiate between these two scenarios and the scenario where the neighbor lies already captured. So we just want to check that the neighbor is not captured. So if the neighbor, as long as the neighbor is not captured, as long as it is still sitting in the right partition somewhere, we are going to insert into the priority queue a copy of that neighbor with a priority value equal to the cost of that edge which we are looking across to see that neighbor. And so the code is actually quite straightforward now in comparison to the previous implementation where we were we had to worry a lot about these decrease key operations, and then being able to access the node and being able to update the node, the node's priority, or the least cost value, the importance of that node, which had to be continually updated. So we don't have to worry about all that, although because we are inserting a fresh copy of each vertex into the priority queue potentially multiple times, our heap size is now going to grow. Our heap size was previously bounded by order n. We couldn't insert more than all the vertices in the graph. Each vertex existed in only one copy. Now every time we see an edge to a vertex, we potentially insert a new copy of that vertex into the heap. So the size of the heap is now going to be order m instead of order n. But there is no decrease key operation here, although we do have to differentiate between meaningful extractions where we are actually dragging a node from the right hand side to the left hand side, and that is the moment where we are adding one more node or one more edge to our growing structure, which will eventually become the spanning tree. And so if our total cost was initialized to 0, this is the point where our total cost has to be updated. So we should say total cost is now going to increase by an amount which is equal to the priority value of the node in the heap which was just extracted, and that is actually the lowest cost cut edge to that node in the priority queue. Future extractions of that node are irrelevant. We would have already ignored those pairs which were extracted, and we would have moved on. But the first time we extract a node from the heap, that is the moment of capture, that is the moment when our spanning tree grows. And so when we exit this while loop over here, we will do so when the priority queue becomes completely empty, and assuming that our graph was initially connected, our total cost here is going to be the total cost of the minimum spanning tree, which we can then return. So let's see what the complexity, the time complexity of this code is. The initialization part is something I'm going to ignore because that had a linear complexity order m plus n as before, so that's not going to change. It's basically the body of the while loop and the number of times the while loop is executed, which is going to determine the overall complexity. So each node is potentially added multiple times this time. We know that the heap will grow to size order m. So how do we quantify the time complexity here? Rather than doing it on a per vertex basis, we will have to try to do the accounting on a per edge basis, because each vertex can now exist in multiple copies. So every time we look across an edge, in the worst case, we might consider adding that edge to the priority queue with some priority value. So if there are m edges in the graph, we are going to do roughly m insertions. Of course, the number of insertions might be much less than m, but I'm just trying to come up with an upper bound on the number of insertions into the priority queue. So m insertions, and every time we insert an edge, it's going to get popped out at some point. So there'll be m deletions as well. So the heap size is order m. How long is it going to take to insert a new edge, or basically a new vertex with the cost of that edge as the priority value into the queue? Well, each operation is going to take log m time, and this has to be multiplied by m because there are m of these operations, and likewise deletions are also going to be order of log m times m, because each deletion is log m and there are m of them. So the total complexity, as you can see here, is order m log m, and because m is at most n square, log of m is basically the same as order log n as we've seen before, so I can write this as order m log n. And if the graph is sparse, then the number of edges m is basically order n, so I can write this m log n as order n log n. And notice that this complexity is basically the same complexity that we had in the previous implementation of Prim's algorithm, and in fact it's also the same complexity that we had for Kruskal's algorithm. So we can run this code on graphs of fairly large size. The only difference is that in terms of space complexity, our heap can now grow to size order m instead of order n as we had in the previous implementation.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today